Hello students, let us discuss linear position invariant degradations. The input-output relationship before restoration stage is expressed as g of x comma y. G of x comma y is equal to h of f of x comma y plus eta x comma y. Now, where if we assume eta x comma y is equal to 0, then input-output relation is g of x comma y is equal to f of x comma y. Now let us see the relationship. If f1 of x comma y is an input, f2 of x to f2 of x comma y is another input, then h of a times, where a and b are a constant, a times f1 of x comma y plus b times of f2 of x comma y is equal to a times of h of f1 of x comma y plus b times h of f2 of x comma y. This property is called linear property, where if we assume a is equal to constant, b is equal to 1, then in this above expression substitute a is equal to b is equal to 1, then this reduces to h of f1 of x comma y plus f2 of x comma y is equal to h1 of f1 of x comma y plus h of f2 of x comma y. This property is called additive property. If we assume f2 of x comma y, the second f2 of x comma y is equal to 0, then that is nothing but only one input is present. Then h of a into f1 of x comma y is equal to, we'll take a outside, a into h of f of x comma y. So this is homogeneity property. Now an an operator having the input relationship g of x comma y is equal to f of h of f of x comma y, then it is said to be position invariant or space invariant if h of x comma y, h of f of x minus alpha comma y minus beta is equal to g of x minus alpha comma y minus beta for the any f of x comma y and any constant alpha comma beta. This definition indicates that the response at any position in image depends only on the value of the input at that point, not on its position. The homogeneity property h of a into f1 of x comma y, if we assume f2 of x comma y is equal to 0, f2 of x comma y is equal to 0, then this property is called the homogeneity property, where f2 second input f2 of x comma y is equal to, then this a will come outside, a into h of f1 of x comma y. Now we'll see the position invariant. Now let us assume g of x comma y. If g of x comma y is equal to h of f of x comma y is the input output relationship, then the position invariant is given by h of f of x minus alpha comma y minus beta is equal to g of x minus alpha comma y minus beta for any f of x comma y and any alpha comma beta. This definition indicates that the response at any point in the image depends only on the value of the input and at that point, not on its position. That is why it is called, now it is linear position invariant. Now let us see the continuous time in terms of continuous impulse response. Now f of x comma y integration minus infinity to plus infinity f of alpha comma beta is equal to delta of x minus alpha y minus beta d alpha d beta. Now we know the relationship g of x comma y, input output relationship g of x comma y g of x comma y is equal to h of f of x comma y. So this, wherever f of x comma y is there, replaced by this one. F of x comma y replaced here by this one, we get this function. Now again, assuming for the moment eta x comma y is equal to 0 and substituting in the above equation, we get here this function. Now if h is a linear operator and we extend the additive property to the integral, then we get this expression. Since f is not dependent on x comma y, we'll take it outside. Function f is not dependent on x comma y, we'll take it outside f of alpha comma beta. Then h of delta x minus alpha comma y minus beta d alpha d beta. So that here this h of h and delta, then they will get h of x comma alpha comma y comma beta. This is the function. So we have used h of x comma alpha comma y comma beta is equal to h of delta x minus a comma y minus b. In this here we have used this one. So in place of this one we have, so equating this to this is the impulse response of h. So in optics, the impulse response becomes a point of light and h of this one, h of x comma alpha comma y comma beta is commonly referred to as point spread function, PSF, point spread function. The name arises from the fact that all the physical optical system blurs or spreads at a point of light to some degree, with the amount of blurring being determined by the quality of the optic components. So this expression is by substituting this one, we get this h of x comma y, we get this is expression. Superposition or Feldram integral, it is given by delta integration minus infinity plus infinity, integration minus infinity plus infinity. So this expression is which is called superposition integral of the first kind. If h is in position invariant, then h of delta x minus alpha y minus beta is h of x minus alpha y minus beta. Now let us see the convolution integral. So we know that convolution integral g of x comma y is f of integral minus infinity plus infinity, integral double integral minus infinity plus infinity, f of alpha comma beta h of x minus alpha comma y minus beta d alpha d beta. In the presence of, if you see, the additive noise is present, where we assumed eta x comma y is a 0, then we can take here, substituting this one at the end, only for the convenience we have assumed it is 0. Now we have considered this one, we get this expression. This is the expression. So if you take the position invariant, g of x comma y is equal to convolution of f of x comma y and y, h of x comma y plus eta x comma y. Now taking this into the frequency domain, j of u comma v is equal to h of u comma v, where convolution becomes multiplication f of u comma v plus n of u comma v. So restoration here we can do first deconvolute, whatever the convolution is, deconvolute, also filter. Image deconvolution is used frequently for linear image restoration. Similarly, the filters used in this restoration process often are referred to as deconvolution filters. Thank you.